Hi, we are going to present a project that we've been working on for the past couple of weeks. Basically, it's focused on a very prominent area of research, which is query spelling correction. Here's a brief overview of what we will be covering during this presentation. We'll be going over some background related to query spelling correction, a brief overview of the main problem behind it, as well as showing you some of the code that we've implemented and the data we have received so far. So why is spelling correction a very important aspect? Because it is pretty much prevalent in every software application and tool that we use today. About 10 to 15% of all the queries that we enter have some sort of error. And here we have a brief overview of the four major categories of errors that we often correct. The first is inward transformations, which is insertions, deletions, and substitution. Usually this is like a one-off character error, like for example, table, we have two B's instead of just one B. Another category is misuse. Usually these type of errors are based on context when associated, when the word is paired with another word. So Capitol Hill it has a different spelling than the word capital, like a capital of the state. And then the last two types are merging and splitting. These are space-related errors where we have an extra space or we're missing a space in a particular word and we want to try to fix that. So you can quickly see these common types of errors. If we had a spelling correction mechanism, it would be very convenient for us and very time-saving to allow the system to automatically correct our error. So now we're going to cover some of the existing methods that have been used for query spelling correction in the past. First is the naive approach, which is basically going through every character of the query and generating all the possible permutations and then see which one is the correct one. But obviously this is a very large problem size and this can be very time consuming. So this is not a very good approach to do this. So next way we make the problem smaller is to only find similar words to those that are in the query and then measure by measuring their editing distance. Now again, even in this approach, it's also a very time-consuming process because there could be a very wide range of similar words that we can find. The third approach incorporates the use of a lexicon, then trying to compute the vector distances between the queries. But in this approach, we have the lexicon has to be manually constructed, and that can be also a limiting factor to how well our problem can be solved. And finally, another more recently used approach is the two-stage approach, which uses like a filter phase, which with the Viterbi and or A-star search, and then a ranking phase. Now, the problem with this is that you lose some accuracy as the potentially best correction candidate can be filtered out during the filtering stage itself. So the end result is you get a suboptimal result. So what are we going to try to do to overcome these challenges is that we're going to try to implement a novel approach that was outlined in a paper recently. And we're going to create a Python module incorporating this new algorithm for query spelling correction. So there are three main parts to this project. First is the generalized hidden Markov model scoring function. Second is the discriminative training of this of the scoring function, and the final phase is to compute the top k corrections. So what is the generalized hidden Markov model? To explain very briefly, basically we have a set of states, usually a pair of currently existing states as well as ones that we've seen in the past. And then we try to omit a word based on a certain specific error model. And we also try to predict our transitions based on previously seen words. And we keep repeating this process from start of the query all the way through the n number of words until the end of the query. So here we have like a basic example of what we would do in order to generate our scoring. First, the example here is a government homepage of Illinois State, and as you can see, there are two potential errors here. Like first is the homepage should actually be one word, and Illinois State should actually be split into two words. So at each word, you're generating one possible state, and then you're also classifying your potential type of error. And in this case, the government actually also has an error. It's missing the N, so we make that correction as a deletion error, and then move on to the next state. Home is correct. Page, technically it is correct, but we analyze the previous word. Home and page can be merged together. And next word is of. Even though it is classified as in-word transformation, it's still technically correct. And finally, you have the Illinois State word that actually needs to be split, and we account for that. So how do we come up with the scoring function? We actually have two feature vector functions. First, for the transition probability, which is based on the bigram model that we're going to use the Microsoft Web Bigram service to help with determining which words need to be merged. And our second feature function is based on the error model that we will be using by calculating the dependency of the state and the observation for our emission probability. And this is particularly useful for in-word transformations where we have mistyping such as insertion, deletions, or substitutions. And finally, now we have our complete scoring function, which combines the previous two feature functions here and here. And we also have two additional weights, lambda and mu, which are initially randomized, and they continually are improved during the training process that we will use for query and spelling correction pairs. And then finally, we have our argmax score, which is proportional to the log probability of a state sequence and its corresponding types for the log probability of Z, the states Z and T for all the given query words.
Implementation. So in a higher level of our implementation, first we generate candidate sets for merging, splitting, transformation for each states of the hidden Markov states, which means for each word in the query we generate those candidates. And second part, the discriminative training. So we are going to use training datasets from Microsoft Speller Challenge, which contains query and correction pairs, to train the two parameters lambda and mu in the scoring function. This part is still under construction. And finally, we're going to use dynamic programming, which is the second algorithm in the paper, to append candidates to each states and then select top K states datasets we used. So besides the paper for our project, we also use another paper called Probability Scoring for Spelling Correction by Kens and William, which provides a confusion matrix of deletion, insertion, substitution, and reverse of characters in words. Here we have those confusion matrix of characters to helping us calculate the score for the emission model. And we also use some dataset of a million bigram, which provide conditional probability of two words, because we are having trouble accessing the Microsoft Bigram API. And also we are using a dataset of English dictionary, which contains 350,000 English words. And lastly, as we mentioned before, we are using the 40,000 query correction pairs. As of now, we already have a working version of our algorithm. And since originally we are planning to build a Python package which contains the algorithm, and any other code bases can import the package and call our function to correct their queries. Here for demo purpose, we are going to use a Python file which take input of k, which specifies the number of correcting queries to feed. Then user input the queries, and then the function will output k number of correction queries. We demonstrate how we implement our algorithm and the project in a more specific way. So here, all the main functions are in one Python file called query correction, and we pre-process our lexicon into words dictionary, and then we also pre-process the million bigram probabilities into hash map. And lastly, we pre-process our confusion matrix of letters for the error model to hash map for easier access. For the processing part, for the query from the user input, we split into word tokens, and then we loop through each word token and generate valid candidate words. And for the candidate generation part, we use a helper function to generate all possible insertion, deletion, substitution, and reversal combination of candidate words using a backtrack function, which will loop through each possible combination within edit distance of 2 and look into the lexicon to get a valid list of candidates and also their score based on the confusion matrix and the error model. We also use a split helper function to generate valid splits of word, which returns list of valid splitting of words and their score, which calculated by the million bigram conditional probability and error model. Then the merging part is a little bit different since we don't need any helper functions to generate candidate sets. We just starting from the current token, we try to merge consecutive word after that and to see if we reach a word in the lexicon. We generate all the possible candidates like for word transformation, split and merge for a word state. Then we use the algorithm proposed in this paper to append the states dynamically until we reach the end of the word sequence of query and return top k possible correction. Here we use a for loop which looping through each state of the input query and also a couple for loop here. And for each state we will append the current candidates and then update the score based on the scoring function. We will do this for merging word, splitting word candidates, and also transformation word candidates. And then we sort the list according to their score, and then get the top k, and we will loop through each state of word until we reach the end, and finally return the final top k correction. Then let's actually run the program to see the outcome. So here we have a user demo file. Execute it. It will take 2 to 3 seconds to pre-process the data sets, and then it will ask user to input k parameter, and then user can input the query. For example, the query from the original paper. Government homepage of United States. Okay, so it will return 7 possible query corrections. So the first one is the correct one, government and homepage of Illinois State. And we can also try to put other queries. Central Park night, if we spell night wrong. Central Park night. Our algorithm is not perfect. We think it's due to the limitation of our training data sets because we didn't use the Microsoft Bigram API. We only got 1 million sets of conditional probabilities between words. So when it comes to words that not often used or the words not in the background, our model cannot score the scoring function correctly. For the next step, we will try to implement discriminative chaining for the two parameters of the scoring function, and also maybe try to utilize bigger data sets of lexicon and background, and utilize the Microsoft conditional word probability API.
In this project, we choose 4 metrics to measure our results: their precision, recall, F1, and top K correctness. So the first 3 metrics are pretty intuitive. Since our application allows users to select up to K number of corrections, we want to evaluate how the value of K affects our result. We also want to compare our result with winners from Microsoft Spider Challenge. So in our dataset, we have pairs of raw query and corrections. So here, we treat the correction as ground truth. And if the raw query is the same with ground truth, we know this one is the correct query. If our corrected query is the same, so we count it as true positive. On the contrary, if our program tries to correct this query, we count it as false negative. And if the query is incorrect and we are trying to correct this query, then this case is true negative. And if we don't correct it, then it is false negative. For the correction test, for each k, we are trying to generate k number of candidates, and if the ground truth is one of the candidates, we consider it as correct correction. And so we run our evaluation on 5,000 queries, and the result is pretty good. We reach more than 0.9 for all the 3 metrics. And we can see with the increasing of the value of k, we could see ground truth is more likely to appear when we have a larger k value.